If you see one of these signs, then you probably should keep away. But it's not the voltage that's going to kill you, it's the current. It's kind of like somebody saying, "Hey buddy, step away from that cliff, the fall will kill you." Well, it's not the fall that kills you, it's the sudden stop. Now, don't get me wrong, voltage is directly proportional to current flow. So anytime you see high voltage, there is the potential for a high current. And it's kind of like that cliff. If the cliff is really high, then there is a high potential that you could fall and hurt yourself. Likewise, if there's a high potential voltage, then there's the potential for current flow. So it is a dangerous situation. Now, why is it that current is dangerous? Why is it that it's harmful to your body? Well, it can burn you, for one, because when current passes through things, those things get really, really hot. Let me show you with a piece of wire. So here's my little drawing of a piece of wire, and let's just say that this wire is made of copper. And these little dots that I've drawn on it are the particles of copper, the copper atoms. Now, when electricity passes through a wire, it's literally electrons that are on the move going through the wire. And those electrons actually bump into the matter that is the conductor, that's bumping into those copper particles and heating up. So it's that kinetic energy which is causing the wire to heat up. Now that turns out to be very useful, because if you now take some of that wire and you form it into the shape of a coil, and then you put a fan in front of it and blow some air towards and through the coil, then what do you think happens on the other side of the coil if we're passing current through it, and the current heats the coil up, and then the air passing over the coil causes the air that goes through the coil to come out as hot air. And why is that useful? I really don't have much use for it, but it's a hairdryer. Let's talk about this hairdryer in terms of some of the problems that you might be asked to solve. When you go to look for a hairdryer in the store, you're going to be looking for one that brags about how much power it is. So, for example, this hairdryer is a 1,000-watt hairdryer. Wow, that's a pretty good hairdryer. Now, what if you work for a company that is designing hairdryers, and you're an electrical systems designer, and they ask you, well, what kind of a heating coil do we need for a 1,000-watt hairdryer if we know they're going to plug it into a 120-volt circuit at home? Well, you would say, oh, well, I think I know how to do that, because you know a little bit about electricity because you've been in Mr. A's physics class. You would draw yourself a circuit for the heating element, which shows a voltage supply for the current that would go through the heating coil. And since the question was what resistance we would need for the coil, and you knew that the voltage supplied at home was 120 volts, you would say, oh, well, I know what the power is, and I know what the voltage is, but I don't know what the resistance is. That's what I'm trying to find out. You would go back and you would look for, say, maybe your boxed equations here P is equal to I squared R, and this is the equation that we use when we were looking to calculate the power dissipated by a heater, and that's exactly what this is. We have R, but we don't have I. But you know Ohm's law, and you know that I is just equal to V over R. So you could substitute V over R for I in this equation. So if I do that, substituting V over R for the I in that equation, then this is the equation that I get. And I could rewrite that, V squared over R squared times R, and that would simplify to this equation. Okay, so now we have another equation that we can use to solve this particular problem. Again, all I did was substitute V squared over R for I in this equation here to get this equation. All right, so do we have the equation we need to solve this problem? Well, not quite. We need to solve this in terms of R, but that would be just swapping the P and the R so that we get V squared over P. So we can calculate the resistance simply by squaring 120 volts and dividing it by the power. And if we do that in our calculator, we get 14.4 ohms. Here's another type of question that you might get. How much energy is consumed by a 1,000 watt hairdryer running for 20 minutes? Well, you know that energy is equal to power times time. That's our standard equation, and if we just have our variables in standard units, then we can plug them directly in. Well, 100 watts is in standard units, so the power is equal to 1,000 watts, and we need to enter time in seconds. Well, we don't have time in seconds, but we do have time in minutes, so you just have to convert, right? So we would say times 20 minutes, and then we would have to use a conversion factor, which in 1 minute there are 60 seconds. Okay, so then if you plug this into your calculator, you get 1.2000000. 1,200,000. Well, that's, what is it? 1.2 times 10 to the 6th joules, because that's our unit of energy. That's a lot of joules. $1.2 million joules sounds like a lot of joules, sounds like a lot of energy, but what is it in terms of that the electric company charges you? Well, the electric company deals in kilowatt hours. There's a meter outside of your house, and this looks like an old-timey meter, but still, even the new ones today read out in kilowatt hours. Well, how does a kilowatt hour compare to a joule? Well, it turns out there's a conversion factor that 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules. And if you multiply this out, then 1.2 million joules turns out to only be about 0.33 kilowatt hours. And typically, I don't know what electricity costs these days, but let's just say the electric company is going to charge you 10 cents per kilowatt hour. That means that running your hairdryer costs you about 3 cents. And that doesn't sound like a lot at all. Finally, in this video, I want to talk about how electric power gets to your house. From the hydroelectric power generating station through the high tension power transmission lines, the power lines that lead to your house, and then eventually get to your appliances in your house. Now, you may have noticed that near these power lines, you will see signs that say high voltage. But 120 volts is not very high voltage. And that's good because we don't want high voltage in our house. They transmit the power at a very high voltage because it turns out that when they do that, they have very low transmission losses. You'll remember from the beginning of this video, we talked about how current flowing through the wire causes the wire to get hot. And we can calculate the power dissipated as heat using this equation right here. Well, there's another equation for power, which is the amount of power that is actually delivered to your home. If we increase the voltage in this equation, then we can decrease the current in order to deliver the same amount of power. Let me say that again. Holding the power constant, if we increase the voltage, then we decrease the current. Now that turns out to be a good thing because in this equation, we want the current to be low because this equation is the power dissipated as heat. We want to reduce that amount of power as dissipated as heat because power dissipated as heat just goes out into the atmosphere and is not being delivered to your house. So if we can deliver the power with low current and high voltage, then we will reduce the amount of losses in the system. Then when we get to where your house is, then we reduce the voltage and increase the current. We reduce the voltage because it's much safer to have a lower voltage inside your house. So following what goes on in the transmission system, the electric power is generated at a sort of a moderate voltage, 24,000. Then using transformers, which we'll talk about later when we talk about electromagnetism and transformers and how transformers work, we can increase the voltage to the power line level, which is 240,000 volts. And then we step it down to 24,000 volts when it's on the poles that go through our neighborhoods. And then one more time we step it down. You may have seen these transformers that are in the poles in your neighborhood right before it comes to your house to get it to 120 volts. So we transmit power. The power company transmits power with high voltage and low current. And then they step down the voltage when they get it to our house to make it safer.